632 meters above the ground, someone is asleep in a hotel bed tonight. Not in a simulation. Not in a concept render. In Shanghai. Right now. The J Hotel occupies floors 84 through 110 of the Shanghai Tower, and it holds a record no other country has touched. The highest luxury hotel rooms on the surface of the earth. Not the United States, not the UAE, nobody. There's a number circulating online claiming this building reaches 200 stories. That's wrong. But here's the thing. The truth China actually built is somehow more unsettling than the myth. The Shanghai Tower stands 632 meters tall across 128 floors, making it China's tallest building and the second tallest structure ever completed on this planet. Construction wrapped in 2015 after 7 years of continuous engineering work, involving more than 14,000 workers. But the raw height isn't even the most remarkable part. The building's twisted cylindrical form, that slow, spiraling rotation you see in photographs, reduces wind load on the structure by 24%. That is not an aesthetic decision. That is a survival mechanism. Without that twist, the forces acting on the building at that height would be catastrophic. And then there's what's underneath. The foundation requires 1,079 steel piles, driven 86 meters deep into Shanghai's soil. That soil is soft alluvial sediment, compacted river delta essentially. The ground beneath one of the world's most ambitious structures is, geologically speaking, mud. A building taller than 2 Empire State Buildings stacked directly on top of each other, anchored into what was once the bed of the Yangtze River. That foundation is holding right now, and somewhere near the top of it, a guest is ordering room service above the cloud line. That guest ordering room service is doing it from floor 84 at minimum. The J Hotel Shanghai occupies the uppermost floors of the tower, floor 84 all the way up to floor 110. And that distinction matters more than it sounds. Commercial aircraft on final approach begin their descent at roughly that altitude. The hotel does not sit near the top of the building. It sits where the sky starts to belong to aviation. Think about what that means for a moment. The lowest guest room in the J Hotel is positioned higher than the very tip of the Chrysler Building in New York. Not the lobby, not the penthouse. The lowest room available to any guest begins where one of the most iconic skyscrapers on Earth ends. A traveler who books the most affordable room in the building still wakes up higher than almost any other human being has ever slept in a permanent structure. The engineering required to make that livable is invisible by design. At those elevations, air pressure drops, humidity behaves differently, and the building itself is in constant micromotion. Gensler, the architecture firm behind the design, and the engineering teams working under the Shanghai Tower Construction and Development Corporation had to solve problems that no hotel had ever faced before. Pressurization systems maintain comfortable atmospheric conditions across all 27 hotel floors without guests ever registering the intervention. Humidity control prevents the kind of dryness that would otherwise make sleeping at altitude feel like spending the night in a pressurized aircraft cabin. Every system runs beneath the surface of the experience, silent and continuous. Getting there is its own event. Dedicated high-speed elevators serve the J Hotel exclusively, traveling at 18 meters per second. From the ground floor lobby, a guest reaches floor 84 in under 55 seconds. That is not a typo. 55 seconds from street level to a point in the sky where clouds form. The Mitsubishi electric elevator systems installed in Shanghai Tower rank among the fastest passenger lifts ever built, and the J Hotel's dedicated cars represent the upper end of that range. Once there, the views operate on a scale that requires recalibration. On clear days, visibility extends beyond 100 kilometers in every direction. The Huangpu River becomes a detail. The sprawl of Greater Shanghai, a city of 24 million people, resolves into texture rather than geography. And on overcast days, something stranger happens. Cloud formations appear below the guest room windows, not at eye level, below. Guests look down at weather systems moving across the city beneath them, which means the building is not just tall. It is above the atmosphere that most people experience as the sky. None of that turbulence, none of that pressure differential, none of that structural reality reaches the guest in any perceptible form. The engineering absorbs it. The experience delivered is calm, still, and quietly extraordinary. The J Hotel is the highest hotel on Earth, and the building it sits inside is doing something remarkable just to keep it that way. Stand at the base of Shanghai Tower on a day when a typhoon is pushing in from the South China Sea and look straight up. The building is moving, not failing, not under stress, in any dangerous sense, moving, by design, on purpose, as a calculated response to physics that cannot be defeated, only managed. At its peak, Shanghai Tower sways up to 1 meter in either direction during typhoon-force wind events. 1 meter. A full human stride, at 632 meters in the air, built into the structure intentionally. Most people's instinct is that a building moving is a building failing. The engineering reality is the opposite. A structure that cannot flex will fracture. The question was never whether Shanghai Tower would move. It was how to control that movement so precisely that guests sleeping on floor 100 would feel nothing at all. The primary solution is a 1,000-ton steel sphere suspended near the crown of the building. This is the tuned mass damper, and it works on a principle that sounds almost counterintuitive. When the building begins to sway in one direction, the damper sphere, hanging on cables and hydraulic systems, swings the opposite way. The mass of 1,000 metric tons moving against the building's motion absorbs the oscillation energy before it can build. Without it, the building's natural sway frequency could synchronize with the rhythm of the wind itself. That synchronization is called resonance, and in structural engineering, resonance is catastrophic. The Tacoma Narrows Bridge collapsed in 1940 from exactly that phenomenon. The damper in Shanghai Tower exists to make certain that never happens at 632 meters above Shanghai. But the damper is the last line of defense. The building's exterior shape is the first. The twisted profile, rotating 120 degrees from base to crown, was not chosen for aesthetics, though the aesthetics work. It was chosen because the twist creates turbulent, chaotic airflow around the building's surface. Wind hitting a flat face generates organized pressure cycles. Wind hitting Shanghai Tower's spiraling exterior gets confused. The pressure desynchronizes. The building fights the wind, not by resisting it directly, but by making it incoherent, stripping away the rhythmic force before it can accumulate into dangerous oscillation. Computational fluid dynamics modeling by Gensler and Thornton Tomasetti engineers showed the twisted form reduced wind loads by approximately 24% compared to a conventional rectangular tower of the same height. That reduction translates directly into material savings, structural efficiency, and long-term safety. Every hotel room above floor 90 is engineered to sit inside that system invisibly. Isolation layers between structural elements and interior finishes dampen micro-vibrations. The floor assemblies absorb what the damper and the facade do not catch. A guest lying in bed during a Category 1 typhoon making landfall near Shanghai feels nothing unusual. The building around them is moving through a meter of arc at its peak. The room is still. That is not comfort engineering. That is one of the most precise structural achievements in the history of construction. Picture a construction site that never goes dark. Not metaphorically, literally never. Floodlights blazing at 3 in the morning, concrete mixers running, cranes swinging loads through the night air while the rest of the city sleeps below. That is not an emergency measure in China. That is standard operating procedure. Weather delays are not scheduled into the timeline. They are engineered around. Rain, heat, cold, the pour continues. This is the machine that built Shanghai Tower, and it is unlike anything operating anywhere else on Earth. The mechanism works because three forces align simultaneously, forces that almost never align in Western construction. Government permits move at the speed of political priority, not legal process. State-owned construction firms carry the capital and the workforce without needing private financing to close. And municipal infrastructure, roads, power, logistics, gets upgraded in coordination with the build, not after it. Remove any one of those three forces and timelines collapse. In China, all three operate in lockstep. That compression is not an accident. It is a system. The numbers that system produces are staggering. China has completed more super tall buildings, structures exceeding 300 meters, in the last 20 years than the rest of the world combined. Not slightly more. Dramatically more. Shenzhen now has multiple towers that would stand as the single tallest structure in most European countries. Guangzhou's CTF Finance Center reaches 530 meters. Nanjing's Zifeng Tower clears 450 meters. Beijing, a city not even known primarily for its skyline, holds towers that would find the horizon of any Western capital. These are not curiosities. They are a pattern repeated across dozens of Chinese cities simultaneously. The most instructive single data point is the Ping An Finance Center in Shenzhen. 599 meters tall, the fourth tallest building on Earth. It was completed in 8 years, from groundbreaking to occupancy. A project of equivalent scale in the United States has no modern comparison, because no project of equivalent scale has been attempted in the United States in the modern era. The Ping An Finance Center was not built by a country that got lucky with a single project. It was built by a country that had already built enough super talls to treat the process as repeatable. Shanghai Tower itself took just under 5 years of active vertical construction after site preparation. For 632 meters, the concrete core rose at a rate that required engineering teams to solve thermal curing problems in real time. Concrete, poured at that volume, generates its own internal heat. And if the temperature differential between the core and the surface exceeds a certain threshold, the structure cracks. Chinese engineers did not slow down to avoid the problem. They developed cooling pipe systems embedded directly in the pores to manage temperature gradients while maintaining pace. That is the edge China builds at. Not reckless speed. Engineered speed. The distinction matters enormously because the buildings are still standing. The machine that built Shanghai Tower did not stop when Shanghai Tower was finished. It is still running. There is a hole in the ground in Chicago that tells you everything you need to know. It sits along the Chicago River, not far from the Loop. At its widest point, the excavation measures roughly 90 meters across. It was dug in preparation for the Chicago Spire, a proposed 610-meter tower designed by Santiago Calatrava, fully engineered, fully permitted, ready to become the tallest building in the Western Hemisphere by a significant margin. Construction began in 2007. Financing collapsed in 2008. The hole sat open and empty for years. The project was formally abandoned. The site was eventually sold and redeveloped into something far more modest. 610 meters of architectural ambition reduced to a construction scar. The mechanism of American supertall failure is not engineering. The United States has the structural knowledge, the materials science, the architectural talent. What it lacks is the institutional machinery to deploy those capabilities at speed. Private financing must be assembled from multiple sources, each with independent risk thresholds. Zoning and permitting processes run through public comment periods, legal challenges, and political cycles. Infrastructure upgrades, the transit, the utilities, the street-level capacity a true super tall demands, are negotiated separately and slowly. Each layer adds years, sometimes decades. One World Trade Center stands at 541 meters, making it the tallest structure in the Western Hemisphere. It is an extraordinary building. It is also a building that took 12 years to complete after a prior decade of political and financial paralysis over what to build on the site at all. The total elapsed time from the September 11th attacks to the opening of One World Trade Center was 13 years. Shanghai Tower, from groundbreaking to occupancy, took 7. No American city has broken ground on a new super tall exceeding 500 meters since One World Trade Center. Not one. The pipeline does not exist. New York's 432 Park Avenue reaches 426 meters and is frequently cited as evidence of American super tall ambition. But 432 Park is a residential tower, a slender column of luxury apartments with a floor plate roughly the size of a tennis court. It is not a civic landmark. It is not a public building. And within years of opening, residents filed formal complaints about audible mechanical noise and building sway that exceeded comfort thresholds. A building that cost over $1.2 billion to construct was generating structural complaints before it was fully sold out. The contrast with Shanghai Tower's tuned mass damper, a system engineered specifically to make sway imperceptible, is not subtle. America built the Empire State Building in 4 and 10 days during the Great Depression. That institutional capacity, that coordination between capital and labor and government, existed once. It produced the most iconic skyline in the world. Somewhere between 1931 and now, the machinery that made that possible was disassembled, replaced by processes that are more cautious, more litigated, and dramatically slower. China did not inherit that machinery. China built a new one from scratch, and the skyline of Shanghai is the proof. Think of the building's skin, the way you'd think of a thermos. Not a single wall holding the heat in, but 2 walls with a deliberate gap between them. A cavity that does the actual work. That is the principle behind Shanghai Tower's double-layer glass facade, and it is one of the most consequential engineering decisions in the entire structure. The system works like this. There is an inner glass skin, which forms the actual weatherproof boundary of the building. Then there is an outer glass skin, set apart from the first by a ventilated cavity that runs the full height of the tower. That cavity is not dead space. It is a thermal buffer, a pressure absorber, and a utility corridor all at once. Start with the thermal math. A conventional single-skin glass tower bleeds energy at a staggering rate. Glass is a poor insulator, and at the scale of a 600D 32-meter building, the surface area is enormous. The cavity in Shanghai Tower's facade reduces heating and cooling energy demand by up to 50% compared to a single-skin design. On a building consuming the power of a small city, that number is not a rounding error. It is an operational cost that compounds across decades. Then there is the pressure problem. At 632 meters, wind does not just push against a building, it hammers it. The force per square meter on a conventional glass panel at that altitude would require glass thickness that makes the economics of the project collapse entirely. The double-skin system distributes that pressure load across 2 separate surfaces. Each panel handles a fraction of the total force. That allows the engineers to use thinner, lighter glass at elevations where single-skin construction would demand material so heavy it would add thousands of tons to the building's dead load. Skidmore, Owings, and Merrill, working alongside the Gensler design team, spent years modeling pressure distribution across every zone of the facade. The twisting geometry of the tower, that 120-degree rotation from base to crown, it was itself partly a facade engineering decision, reducing wind load on the glass by approximately 24% compared to a conventional rectangular profile. And then there is the detail that almost nobody talks about. The facade captures rainwater. The outer skin channels precipitation through a collection system that feeds directly into the building's internal water recycling infrastructure. The skin of the building is not just a wall, it is a utility network. At 632 meters, every surface either earns its place or it doesn't. This one earns it 5 times over. Here is the thing about Shanghai Tower that the photographs never quite capture. Getting to the 120th floor is not just a question of height. It is a question of physics that had to be reinvented from the ground up. The elevators inside Shanghai Tower travel at 18 meters per second. That is not a metaphor. That places them among the fastest passenger elevators ever installed in a permanent structure anywhere on Earth. At that speed, the cabin is covering roughly the height of a 6-story building every single second. The human body was not designed for that. Rapid altitude change at 18 meters per second would cause the kind of ear pressure discomfort that makes passengers miserable. So the cabins are pressurized, using the same principle that keeps commercial aircraft cabins tolerable at 35,000 feet. The elevator is not just a box on a cable. It is a pressurized vehicle. The double-deck design moves 2 floors simultaneously, having the number of shafts required and reclaiming structural space that would otherwise be consumed by mechanical infrastructure. And the emergency braking systems, the systems that must arrest a cabin traveling at full speed without injuring a single passenger, require deceleration curves calculated to the millimeter. The elevator program alone demanded a dedicated engineering team and consumed a significant fraction of the tower's total mechanical budget. What that means, at the highest level, is this. Shanghai Tower is not a building with a hotel inside it. It is a city compressed into a vertical column with every system, the skin, the structure, the movement of people, engineered as a complete and interdependent machine. The next tower that tries to surpass it will have to beat every one of those systems simultaneously. And somewhere right now, a team is already drawing the plans. But here's what the building is really saying. Every foreign executive, every diplomat, every investor who checks into the J Hotel and feels Shanghai shrink beneath them is receiving a message that requires no translation. If China can engineer this, what else can China do? The 200-story myth spreading online is actually the point. The world's perception has already outpaced the reality. Subscribe for more stories like this one.